Hello everyone. In this presentation, I'll talk about electric vehicle impact on grid. My name is Mizan Chaudhary. On my first slide, you can see a very basic electric vehicle from Bangladesh. This electric vehicle is very simple. It has the front wheel from a motorcycle and the back is designed for it. It has battery and electric motor and it works. But fun fact is this is illegal in Bangladesh because there is no charging station in Bangladesh for electric vehicle, and this kind of vehicle is not charged at home. They are charged at marketplace, like a market, and they steal electricity from the market's transformer, and so that is illegal. But this is not the case in USA. You have to pay for electricity. So we'll discuss about that as well, about the cost. So in this slide, you can see US energy consumption in 2019. If we look at transportation sector, we can see that 37% of total energy produced in USA is used in transportation, and 91% of that comes from petroleum. As we are moving forward to a greener future, the 91% of petroleum is a matter of big concern. If we look at electric power sector, it is a mixed fuel such as natural gas, coal, nuclear and renewable energy sources. If we increase electric vehicle, the real source of transportation energy will be diversified and will greener as time passes because of increasing number of renewable energy in the future. So that's why it is important that we support electric vehicle. In this slide, you can see a difference between a gasoline powered vehicle versus an electric vehicle. Electric vehicle pretty simple in terms of hardware. Electric vehicle main component is just battery and electric motor. On the other hand, gasoline vehicle is much more complex with the combustion engine and transmission and all that. But you can see all the parts in the picture here. So electric vehicle needs charge and it costs money, so we should look at the levelized cost of charging. Levelized cost of charging will depend on the rate of electricity and also cost of installation of a charging device or a method of charging. So in this map here, we can see levelized cost of charging in different states of United States. Darker color is referring to higher prices and lighter color showing cheaper. Some states has around 12 cents per kilowatt hour and some state has 31 cents per kilowatt hour, like in Hawaii. So levelized cost can be different. We can see in California the cost is 18 cents per kilowatt hour, and in Texas has 15 cents per kilowatt hour. So we'll look in the next slide how that affects. So everything needs incentive. Why would you consider shifting from gasoline powered car to electric car? And you can see that on average a person can save from a minimum of $4,571 on average to $12,048. And for this calculation, 15 years is said to be the expected lifetime of each vehicle. Here you can see that despite of high levelized cost of charging in California, that California has the highest amount of cost saving in the United States. Uh, then Pennsylvania, we can see that although the average cost of electricity was not so much, but because of I believe gas price being slightly higher, it's good amount of saving in Pennsylvania. Then in Texas, 6,382, Tennessee, 6,222. Average, you can save 7,758. So that's a good number over 15 years. So that's about $500 every year. That's not bad at all. And you can probably save even more in the future if the gas price goes up, because this is comparing to gas price. So then let's get into the main concern here, the impact of electric vehicle charging. So one research paper suggests that charging current can be 10 amp for standard, 30 amp for fast charge. Slow charge from single phase takes about 6 hours for a average battery to get full. In this paper, we'll look at three scenarios: electric vehicle charging effect in low voltage grid in Hungary, electric vehicle charging effect in low voltage grid in UK, and electric vehicle charging effect in medium volt grid in California. So in this slide, you can see different vehicles and their battery sizes. Tesla being the highest, biggest battery size, and some other vehicles are hybrid, so that's why they have a smaller battery size, but these are just for reference. Here we'll consider electric vehicle charging in low voltage grid in Hungary. So low voltage meaning here we have a 400 volt feeder, three feeders, feeder 1, feeder 2, feeder 3. We have a transformer of 0.4 MVA, converts 10 kV to 0.4 kV. In this graph we see the electric vehicle arrival time, and the peak time is 1800 hours 6 p.m. and on the graph on the right you can see the peak power demand is at 2000 hours 8 p.m. and that's pretty obvious because people tends to come back home and turn on their appliances, and that's when the peak power occurs. So in this slide we will consider uncoordinated charging, meaning people charge their vehicle whenever they want, and versus delayed charging, when people don't charge at the peak power demand time, rather they charge it in off-peak hours. So if everyone charges whenever they want, although it says whenever they want, but they're most probably charging right after they come back home, they relax for a little bit and plug in. So then the peak demand gets pretty high and exceeds the 100% rating of transformer, and that's not good for the utility because that's gonna reduce the lifetime of the transformer. So at 60% it's not good. But if the people delay their charging time, if they delay it till at least 2200 hours, then that peak is gone, and then people start charging, then we are, even at 60%, we are within 80% of transformer rating. That is very good. On the bottom we can see the voltage deviation. Voltage deviation is the nominal or the rated power rating, rated voltage versus the actual voltage. And in many countries the electric those power quality laws are stricter, and they need to maintain a certain amount of voltage deviation. And with uncoordinated charging, it exceeds that. I believe it's 5% for Hungary, so it exceeds that, but with delay charging that problem is gone. In this slide we have summary of the findings on the electric vehicle charging effect in low volt grid in Hungary. So for uncontrolled charging, we can see on the right that the total system loss is higher in all three cases, and at 60% it's quite concerning. And with delayed it gets reduced by some. So, and regarding that, at 20% electric vehicle penetration in the grid would result in a peak increase in the load demand of 21.3%. That's for uncontrolled charging. 60% penetration level of electric vehicles would lead to 64.9% increase in the load demand. 60% electric vehicle penetration, the network experience overloading of some of the components, the transformer, the fast feeder. But for delayed charging, everything everything stays within normal rating. Now we'll consider the case of electric vehicle charging in United Kingdom. Experiments done in similar situation with 400 volt feeder. In a study, they found that electric grid in United Kingdom is adequate of 10% penetration of electric vehicle. If it goes beyond that, then problem arises. This study shows similar effect of unscheduled and scheduled charging on the peak demand as seen in Hungary. That means if it's uncontrolled, if it's unscheduled charging, grid encounters many problem. But if the charging is controlled, then we can proceed with higher percentage of electric vehicle penetration. So for this study, they use this model, and basically it's multiple 400 volt feeders, 400 volt let's say substation that has one feeder each. That's what making the study easier. This is a typical daily load profile for domestic load in UK, and the peak is on at 6:30 p.m. similar to Hungary. So here we have 4 graphs. The first one is voltage profile for maximum loading and EV electric vehicle in charging mode. So in this study, on the previous study they only experimented with electric vehicle getting charging, but in this one, in addition to that, they're gonna consider when electric vehicle is in regeneration mode. So when electric vehicle is feeding the grid, this is something called vehicle to grid technology. So they're gonna experiment with that too. So what happens when the grid has maximum loading and electric vehicle is in charging mode? At that time, some substation, you can see that they are so in UK for so the lower limit is 5% of the nominal voltage, and in this case it's getting close to 0.94 per unit. So this is in violation. So 30% electric vehicle with maximum load, some substation goes below that 95 even with load tap changer. In this one they have minimum loading and electric vehicle is in regeneration mode. So then some substation see that voltage goes even above 10% limit. That's in violation. So many substation sees that even with load tap changer, maybe with load tap changer working at 20%, somehow it manages to stay within that 10%, but at at 30% electric vehicle penetration, it goes above that 10%. So that's in violation. This one is voltage profile for minimum loading and localized electric vehicle in regeneration mode. So that is a randomly taken. Different feeder has different electric vehicle and different number of electric vehicle randomly, and The study shows that um, in this case, even with 20% electric vehicle, the load step changer is unable to bring that voltage down. Compared to in this picture, this is voltage profile for network with 3 electric vehicle park. So substation 7, 8 and 9 has electric vehicles park charging station, so this is kind of controlled, and in this case even with minimum load, maximum load, everything stays in between that bandwidth. So this is then we are going to look at another situation, electric vehicle charging in UCLA, University of California, Los Angeles, California. This is a kind of differently because this only includes a charging station in UCLA, different charging station in UCLA. So 90% of charging events transferred less than 12 kilowatt hour. 67% of the time electric vehicle connected was for less than 4 hours. 87% of the time electric vehicle connected for less than 7 hours. Energy peak brought by electric vehicle charging is 7 to 10 a.m. when users came to work. Electric vehicle usage peak can be offset by installing PV panels and solar system. So this is easier because probably the power demand peak doesn't occur at 7 to 10 a.m. so they're good to go, and that peak can be offset by using solar panel because at 7 to 10 a.m. there should be good amount of sunlight. So then what are the solution or the mitigation to this problem of electric vehicle impact on grid? One solution is V2G, vehicle to grid system, that can manage the power load by discharging the battery into grid at peak time and charge when there is low demand. Intelligent schedule of charging helps to manage peak load and shift the load curve. Direct coordination of charging and discharging by smart metering and intelligent control and communication is necessary for that. And also we need to integrate DER and V2G technology, which can even bring better power quality when using DER. V2G can give that stability to the grid. So this one is a diagram of vehicle to grid technology. We can see that these are different kind of um, generation source of electricity. Then we have transformer, transmission going to distribution going to houses or charging location. Then we have smart meter, then we have charging connector, and then we have the electric vehicle. Now this one, now by using smart meter we can do G to V, that means grid to vehicle power flow, or we can provide that V to G power flow, which is vehicle to grid. So this basically this is going to be plugged in for most of the time when in charging, and when the grid needs that support from vehicle they can get it, and when it's good time for vehicle to get charged, it will get charged. But in this process there are some drawbacks as well, because battery is continuously charging and discharging, that will um, reduce the lifetime of battery, and might be some issue with communication as well, because if communication is lost then this system's not gonna work. Also it needs support from the utility because they need to provide smart meter, or not all the states have them, and the utility needs to come up with a robust plan considering all this. So in this slide, I have a diagram with different kind of standards required for electric vehicle to follow. National Electric Code, that's for charging, ISO battery standard for battery, then for charging connector SAE J7, J1772. For smart energy, they have Zigbee Smart Energy 2.0, IEEE 1547 for distributed energy resources, then some IEC standard for other equipment to follow, and other standard you can see. And these are the reference for my presentation. Thank you, everyone.